All right, welcome to EE 420, ECG 620. Uh, let's go through how to get all the course info and all the logistics and things that I've changed this semester just for you. Okay, so first thing, the website. If you didn't get my email with the link, CMOS.edu, you can click right here and go to courses. Instead of doing that, you can click also on my web page, and then you can see my office hours are listed here. Yeah. Yeah, I went to Australia and New Zealand, but it's been couple years. Anyway, I always rotate the pictures, right? I got to have something different to look at than the same old picture. Like I went and met Britney Spears this January a couple weeks ago, so I took a picture, but it ended up being a bad picture. See? There it is. All right. So, anyway, to go to the courses, so you'll see I have extra office hours this Friday, day after tomorrow, and I'll talk about that more in a moment. If you've taken classes with me, you know I travel a lot, basically every week. So, all right, so click on courses, and then here's our course web page. Here's the 420 web page. So let's go through this nice and slow. Course lecture notes will be here. When I have a class right after this one, and then I have office hours after that. So as soon as possible, I will scan the notes, and I will post the video of the lecture here. If you've taken classes with me, I'm boring you, and you know how this works. I will have an extra lecture this Friday. I want to get ahead of the game just in case later in the semester, in the likely case, I have an unavoidable time I have to miss. If you've taken my classes also, you know that I tend to not rush and be frantic at the end. The ends kind of taper out smoothly so that you can focus on other work, but that means that the beginnings are more intense. Okay. If you can't attend the lecture this Friday, day after tomorrow, there won't be any homework assigned or due on that day, and there won't be a quiz this Friday. If you can attend, it's good. If you can't, watch the video this weekend, okay? Because I like to think, and you can talk to other people, dude, yeah, come on. But we'll discuss that more in a moment because I solved that problem. We're going to take care of that. We're going to adopt the Hogwarts method of awarding and taking points away from the houses. So, if you can attend Friday, do it. If not, watch the lecture on the weekend. My lectures, as you'll see, are generally not a waste of your time, but you'll find out on your own. And it's generally not a good idea to skip them because I tend to cover things that are important, like what will be on the quiz and all those things. The homework assignments will be posted here. Pretty much you'll have homework due regularly. See these two homework assignments, A931 and 932? Those are additional problems. They're not from the back of the book. So what you do is if you go click on the book web page, you can go down here and download the additional problems. Now let me head off any problems right here. You go to do the homework, and you downloaded this at the beginning of the semester, and their problems are not there. I assigned 931 and 932, and the problems only go up to 930. Well, that means that I made new homework problems and post them on here, so you have to re-download the zip. Okay, I don't just use the same homework problems over and over. I make new ones up every semester. Now, I might use some of the same old ones, but when I make the new ones up, you'll have to go re-download the file. Does anybody not follow that? A couple of other comments. The solutions, they're posted on the web. You can find them independent of this, but they're here for every single problem in the book. So if you're having problems working some of the homework that you have in this one, there are examples, literally hundreds and hundreds of examples here that you can look at, okay, to set you up for success. Also notice that If you have problems, the previous year's course web pages are posted here, like 420 here, and then I taught it as 422 the second semester I was back at UNLV. You can go rewatch the lectures there or get the notes and watch the solution to the problems. The problem with putting PDFs here, so there's one issue. If you have um, you don't have Microsoft Office, and say you do and you don't have the equation editor installed, then you'll go and there'll appear to be an equation there and it will be missing, right? So the reason I don't want to put PDFs there is because then I have to constantly not only generate new homework problems, load them in the zip, upload them, but then I also have to make PDFs of the new homework problems, and I'd prefer not to. That just ends up being an unreasonable use of my time. So what I would suggest is that you either find some software that'll translate this, like OpenOffice or something like that, or you get somebody in the class to send you a copy of the homework once they get done. I mean, if it really gets to be a hardship, I'll spend the time, but I mean, you'll find out if you haven't taken another class from me that, holy crap, all this stuff adds up to a tremendous amount of time. And the last thing I want to do is, well, so-and-so can't use Microsoft Word, so can you put it in Word Perfect? Can you put it in PDF? Can you put it? No, I can only do so much. I mean, within reason, all right? So if it gets to be a problem, let me know, but hopefully it won't. There is online PDF converters too, where you can upload a file and it'll convert to PDF and download. So that has nothing to do with the operating system that you're on. Yeah. Okay. So like I said, you can go look at old lectures. You can see what, if I worked quizzes, what the quizzes are. Now, all this is here. You'll see the notes. You'll see I work quizzes once in a while, tests, whatever. It's all available, but you have to put effort in, right? It's not magic. I mean, it's nice to have it, but it's not like it just magically the information goes into your head. You actually have to look at it and study. Okay. So these learning aids are great, but they're not. They're still, they're only to help you, but you have to help yourself. So I'll probably in the next couple days assign homework that's due on Wednesday. So we'll see how that goes on the weekend, okay? Let's see. We're going to use LT Spice in this class, and I'll probably do some examples today talking about that. When I do examples, I will post them in this file so that you can download. So let's go ahead and fix that right now. So what that means is when I do an example in class, if it's not just something directly out of here, I will save it in this folder. So I'm going to make a new folder and call it EE420, 620, and then at the end of the lecture, I'm going to zip up the examples we did in class so that you have them and you can use them on your own. Does everybody follow that? All this taking a lot of my effort, all right? So don't come and say, well, I don't know how. Did you do anything to try to figure it out? Okay, because I'm doing stuff for you to try to figure it out. All right, textbook is this one. Third edition. We'll talk about the policies in a moment. Teaching assistants, Yeon. He's over in 310. Let me see. Does he have his office on here? It's in TBE 310. If I think about it, I'll ask him to put his office number here. It's where the grad students are sitting. Class time 1 to 2:15. Course dates now until May 6th. Location here. We have 3 holidays. We get Washington's birthday recess and then spring break from instruction. Course content, you're basically going to learn how to design analog integrated circuits. So by the time you're done with this class, if you've done well, you'll know how to design an op-amp. Okay? Yes? No, through the semester, I'll go and say, oh, I covered this. Let me add a homework problem on that, and I'll write one up and put it on the web, and then it'll be posted right in this zip file, so you have to re-download it. Whenever you go to work a homework problem and you don't have it. Yeah, I'm not changing ones that are inside. It's only adding to the end. Okay. Question? Questioni? All right. So, let's see. Here's the grading, midterm, homework quizzes. We won't have quizzes every day, but you probably might think it feels like every day. Okay, now our policies. No laptops, internet appliances, smartphones used during lecture or exams. Don't put up your backpack on there and then hide it, and then I get the students complaining to me. I can see it, and especially when I call your name out in class. I mean, it's ridiculous, all right? So just so now, when I see that, I'm going to start taking points off. So when you ignore me, which I take as a sign of disrespect, and you ignore me over and over and over again, I will inflict massive amounts of pain on your score. Okay, so now I'm not a toothless lion like I have been in the past, relying on the niceness of the students to follow the rules. Rather, now we will be nice, but then when they don't get it, we will take care of business. Of course, that may go the other way. If you are doing something that's good and contributing, I might go ahead and add some points. You know, I like the Hogwarts method, you know. All right. Any questions on this? So don't do, this is my favorite. Instead of watching, it's like, yeah, I can't see you playing with your phone. All right. But I was checking the course web pages. What's wrong? I was watching last time's video because I like to watch videos and the current one at the same time. Okay, if the exam or quiz is open book, then only the course textbook can be used. So, and you probably got it from me in the email. Last year at this time I taught 320 microelectronics, and I actually had a student that would not buy the textbook, and I was nice. Oh yeah, I'm gonna get it, and I would put it up on. I would put the problem from the book up on the dot cam, and I would project it for him. And then after a while, I'm like, "This is ridiculous. I told you to buy the book. You're ignoring me." And he goes, "Well, I was going to buy the book, but as soon as you started projecting the problem up on the dot cam, I changed my mind and decided not to." And I'm like, mental note. And then he dropped the class. Okay, so if you're trying to, I personally don't understand this thing with, you mean I'm going to go to college and I have to buy books? Or I'm going to go to college and I have to attend class? What's up with that? All right, so I think you need to buy the books, you need to attend the classes, you need to put the effort in. And the other thing you'll find out is I joke a lot about getting your money's worth, but you paid a lot of money for this, and you won't know how much money or how hard it is until you start paying back those student loans. When you go for job interviews, you don't know what you're going to be asked or what's going to happen down the road, and I don't want you going in there having spent $30,000 and have no skills that you can put forward with just a piece of paper that says, "Hey, I got a degree, hire me." Okay, people don't need that. They need you to be able to do something, okay? And so that's the way I approach things. You paid for something, I want to give it to you. All right. Okay, I'm not going to return the final exam. I don't want to accept late work. Say you are going to a job fair in Minnesota, and I'm going to miss class. I don't care. If there's a quiz, I don't care you miss it. If you want to turn in the homework, email it to the grader, copy me on it, and do it before it's due. Okay? Take care of business. Don't come in and say, "Oh, this." I'll tell you why I have this philosophy too. Last semester, and I was really nice. I'm busy because of X reason. Can I take the quizzes late? Can I take another quiz late? So they have like 3-4 quizzes that they're late. And then there's a few cases where the student actually makes it through the class, but in the majority of the situations, the student doesn't make it. They get so far behind they can never catch up. So if I start to be nice, that ends up hurting the student and they don't make it through the class. So I'm not going to hurt you. Okay, so turn in the quizzes on time, turn in the homework on time, be available for the quizzes. Just follow the rules. I won't return the exam at the end of the semester. You'll see that I'm very generous. But by the time you go into the final, your grades, I mean, you're at 75% and your final's another 25. I don't need you in there whining to me, oh, I'm not going to get a job, or boo-hoo, give me a C instead of a C minus when I got a 62 in the class or something. Because it's, from my point of view, I put a tremendous amount of effort into the class, and I don't like it that you come in and you waste my time after I've put so much effort in, and you've put so little effort in to try to get a passing grade, and it's not fair to the other students that did put the time in. Now, having said that, every semester that I'm here, 30% of the class, in these classes, not my 700 level, but 30% of the class do not get a C or better. So if there's 30 people in this class, we're looking at 9 people will not get a C or better. Okay? Every semester that I've been here, it's been like that. So, I'm not one of those people that hand out grades. You have to actually earn it. You have to know what you're doing. And I don't feel bad if I give you a C minus or lower, because that's what you earned. I didn't determine your grade, you did. Okay, so know that right up front. I hope this semester things change and I give everybody a C or better, but hasn't happened yet. Okay, so don't complain to me about this. If you have problems and you need to leave in the middle of the lecture, or you have problems getting to here on time for some reason, let me know. But if you just constantly come in late, what am I gonna do? Hogwarts, man. I'm gonna Hogwarts you. Okay, so it's disruptive, and it's not fair to the other people that are planning and getting here in time. Now, having said that, this is my 25th year teaching, and there's been situations where there's been people that have had problems. Like I had one student that had cancer, and he needed to get up in the middle of the class in the middle and leave regularly. Just tell me what's going on, all right? I'm not saying you can't do it. I will say sit by the front so you can get out easy with a little disruption. Don't sit right here and then walk, right where everybody can see you. But there's things that happen, and I've been through a lot, so I know there's issues. So just communicate with me. All right, so cheating and plagiarism. I'm a hard ass with this, so if I find out you turn in homework or you copy on the quiz, I'm not one of those people that just sleep and put on my music and watch videos during tests. I will pay attention. Just do your own work and do the best you can. And, I'm not here to trick you. I'm here to help you. So I'll try to make sure you're successful and you get something out of the class. All right, this is a big one. So I've got like 70 students this semester, plus people all over using the books and stuff. So please don't email me questions. When you say, hey, I don't understand in problem 9.1 what is meant by, I don't remember what the problem is, but solve for R1. And then I answer you individually because you emailed me. Everybody else in the class doesn't get to hear the answer or the question. A lot of times people will not email me because it might be a stupid question, I might be not understanding, or whatever the reason. If you have questions like this, join the Google group and email the Google group the question, and everybody gets the response from me, or even better, another student in the class, and it saves everybody's effort and time. If you do not want to be recognized when you email the group, anybody can join. You can make up an email alias and then join the group under the alias if you're ultra shy, okay? I've had students do that in the past. If you've been a member of the group in the past, you're still a member. However, at the end of each semester, I change everybody's permissions back to moderated so that you don't get all so you can't post automatically, and moderated and you don't get the emails. So if there's 1,500 people in the group or whatever there is here, which I think there's some large number like that, you're not blasting an email out to 1,500 people. You're blasting it out to the people that went this semester, that joined, so however many that is in the class. So if somebody says, hey, we got a take-home quiz, or we got a problem, and I don't understand this, and I go, oops, I made a typo, and I respond to the group, and I say, I made a typo, it should be this, this, and this on the problem, and you know what? You aren't joined the Google group, and you don't get a response. That's your fault. Okay, you need to join the group. You need to be available and get the response for, what the questions are. And again, it's all there to help you out and to ensure that the information flows easily. If you have questions for me and they're only for me, you need to talk to me in person. I really hate email, just because I could sit there all day and answer email, all right? And whenever I need a form signed from somebody, I very much prefer taking the form, leaving my office, and going and seeing that person, because I like personal interactions more than chatting via email, all right? I think that sucks, okay? So come and see me or whatever. Now, having said that, if you see me walking around the hall, don't ambush me, all right? Because a lot of times I got things going on, and do you have time to answer a question, something like that, or not what some students do. Hey, I got this problem. You need to like I'm on my way somewhere. Be polite. All right. Does anybody have any questions on any of this stuff? What's happening on Friday? Extra lecture. What's due on Monday? What's due on Wednesday? Will we have a quiz on Friday? Will we have one on Monday? Probably. All right. Let's see. Any other thing I should cover here? For the tests? Yeah. Make do, man. Come early and get that desk in the back. All right. So since there are no questions, textbook. I didn't cover that. I did a little bit. Where's the textbook? Where? Yeah, textbook. Don't come in with a PDF on your Kindle or something. All right, so let's get going. All right, so what we want to do in this class is, bottom line is, we want to learn how to design integrated circuits. And I want to not only make sure you know how to design integrated circuits, I want to make sure you have a feeling for what's going on, so that when you look at a circuit, it's not like looking at an equation, but you have some feeling for, oh, this is happening, this is what I'm doing, those kind of things, all right? So I'm going to start out with some really fundamental stuff and do some SPICE simulations. And one of the first things I always start with is the concept of a current voltage plot. And if you've taken electronics 1 from me, and maybe even the digital IC, you may know I've covered this already. So why is it that current's on the y-axis and voltage is on the x-axis when you do IV plots? Like if I plot the diode curve, it does this, right? So why is it that when I plot in electronics, I do current and voltage? Yeah, so voltage is a controlling variable, right? So you change the voltage, it changes how the current flows. So a lot of times I apply a voltage and I look at what current flows, okay? So we're going to look at the IV plots for basically every electronic component. So first thing I want to do is I want to do the IV plot for a voltage source. So here's a voltage source. Let's just call it V. And let's say in this case V equals 1 volt. And I say plot the IV curves for a voltage source. What is it? Yeah, I can't change the voltage across the voltage source. Now here, this is the voltage I'm plotting and this is the current. The voltage from these two nodes is fixed and I can't change it. It's held at this potential, but I can change the current, right? Simple way is just put a resistor across there and change the resistor value. So if I plot the IV curves, I get this, 1 volt. And if V was -1, then I put it over here and I'd get -1 volt. If I take the same thing and I plot current, let's do it like this, just to be a little confusing. And let's say it's 1 milliamp. And I plot plus minus V, and I call this I. And I ask you to plot the IV curves for that current source. Yeah, since the I here is equal to minus 1 milliamp all of the time. There's no deep thought, right? The current that flows through this is always 1 milliamp in this direction. So it's like this. Did I mention I'm going to take points off for sleeping too? All right. Okay, because I'm not boring. Just ask me. All right, what should I do next? Resistor. So I look at the resistor and I go, okay, I got a voltage across there and then I got a current flowing through there. How do I relate the X is voltage, the Y is current? What is the relationship there? I'll put up here Y equals mx plus b from my 8th grade days learning how to plot a line. What is it? Yeah, so it's a diagonal line, but let's write the equation. So Y would be current is equal to, can you see that green color all right? Wait, current is equal to X, which is V divided by R. So when I plot the line, I get this. And what's the slope? 1 over R. Let's plot two more things and then we'll move on to actual components. Does everybody see? When I look at an IV curve and I say, hey, this looks resistive in this area, and I point to that area, that if it's got a slope like this and I say it looks resistive, then the resistance is going to be 1 over the slope. If I go, hey, it looks like a voltage source here, what's the resistance of a voltage source? What's the rise over the run? Infinity. So what's the resistance, internal resistance of an ideal voltage source? 1 over infinity, or 0. Same thing here at the current. 1 over, or 0 over infinity, 0. Or infinity over 0, sorry, is infinity. The resistance is infinity. So let's plot two more things. What other simple components or things that we could plot here? How about an open? What would an open look like if I plotted it? So here's an open. Yeah, it's just this, right? The current is 0. It's like that, right? I can never get current through there, but I can change the voltage across there. I can put whatever voltage I want right there. Okay, and so since I'm the king of predictability here, what's the next component? Short. So I take a short. Can never change the voltage, but I can change the current. So this is a short. And this is an open. Looking good? Okay, so remind me, what's a current source look like? A flat line like this, right? So let's go look at the IV curves for a diode and then for a transistor. So let's go and take, and I'm going to plot for a diode, V diode, I diode, and then here's my diode, which I've got my two little components here. And I ask you, this is one where you might want to, if you don't know how to plot the ID curves for the diode, you are in for a rough ride this semester. So, which side is reverse bias? This side or this side? This side, right? And that means little current flows. So here I get this. So tell me, what does the diode look like over here when I reverse bias? An open. And that's the way you should think of it in your head, is when I reverse bias this diode, it behaves like an open. I don't get any current through it. When I see it in a circuit and it's reverse bias in my mind, I'm going to think open. It's not going to confuse me, just an open circuit. And when I forward bias the diode, I start to get what shape of curve? Yeah, I get something that looks like this, where this is about 0.6 volts or so, 0.7, something in that range, right? Okay, so if I put a lot of current through the diode, what does it approach? What's that? If it starts to go, if I keep putting more and more current, what does it start to behave like up here? Well, more precisely, voltage source, right? Because it starts to get vertical. I can change the current, but I'm not changing the voltage across the diode. And that makes sense because I know if I forward bias the diode enough, I get 0.7 volts across it. I can change the current, but the voltage doesn't change very much because of that exponential behavior. Does everybody follow that? Okay, so now what if I come down here and I focus only on this area right here, and I say, well, what does the diode look like right here? Looks like a resistor where the slope is 1 over the diode resistance. So I could actually model the diode in this area right here as the following. A resistor and then a voltage source of 0.6 volts. So in this area right here, if I have 0 current flowing through the diode, the voltage is 0.6. As I increase the current, I get a voltage drop because of the diode's small signal resistance. We'll cover this later. And I get a curve that looks like this. So I say the diode behaves like a voltage source and a resistor. Now, why is this important? When I'm analyzing the circuit, I don't want to think of the diode in that equation. What was it? ID equals IS times E to the V diode over NVT minus 1. I don't want to think that complicated. I got to do things that people use, something practical. So I got to think of the diode as something that makes sense, like a voltage source and a resistor. Okay? Any questions on this? Let's do the MOSFETs. And I'm going to cover the IV curves later, but I just want to give you should have all seen IV curves already, but just I want you to plant in your heads what's going on. So this is ID versus VDS, and let's say I get a curve that looks like this for VGS greater than the threshold voltage. And again, I'm going to cover this so you don't go, I don't understand that curve. We went over it in electronics. I never really got it. I'm going to cover it, okay? Right now, just take my word. This is the curve for those situations, okay? Of course, if you took 320 from me and you say that, I might start crying, but that's okay. So, what does the MOSFET look like? So here's my 2 terminals. There's the drain, there's the source, there's I. What does the MOSFET look like in this area right here? A resistor. Okay, so it's a resistor. We'll call it 1 over R channel. So when I think of the MOSFET, what I'm going to think of it as in that area is just a resistor R channel. I like circuits with just resistors because I can understand what's going on and they're easy to analyze. Everybody follow. What do I think of the MOSFET over here? Let's say it's perfectly flat. What do I think of the MOSFET as over here? A current source. And if I come over here and I call that current ID sat, I think of the MOSFET as a current source. Now, let me see. It's only a current source when it's in this area. Oh, what was this area called? Saturation. And it's only a resistor in this area, and this area was called, give me 3 names. Triode, linear, ohmic. Just to be confusing. Now, wait a sec, the actual curve here looks like this. It's got a slope to it. I want to model that. I want to model that slope, and I want to prove it in SPICE. So I'm going to put what the model is, and I want to prove that it looks like that in SPICE. So I know I've got this current. Let's just say this was 10 microamps. And let's say over here let's say this is 1 volt. It's at 10 microamps. And let's say here it's at 2 volts and it's at 11 microamps. So the voltage across this is changed by 1 volt, and I get 1 extra microamp. So by applying a potential between here and here, which I'm going to call VDS here, by applying a potential across here, I'm increasing the current by 1 microamp. Well, if I don't apply any potential, I'm right here with the DC voltage, and if I really wanted to complicate it, I could put the DC source there, but I'm not going to worry about that right now. I go 1 volt up, and I've gone up 1 microamp. Here I've got 10 microamps flowing. How do I apply 1 volt here and get an extra microamp to flow? A resistor. So if I have a 1 meg resistor and I put 1 volt across it, what's 1 volt over 1 meg? 1 microamp. So I've modeled this MOSFET operating in the saturation region as a DC current source in parallel with a resistor. Now I'm going to simulate this right now and prove it. But before I do, I've got a question. If I then took and applied an AC signal across here, and I ask you, let's say I apply an AC voltage of 1 volt, now let's say at 1 millivolt, keep it small. How much AC current flows in that DC source? How much does the current change here? 0. We don't get any current flowing in that. Does everybody agree? How much current do I get flowing in the 1 meg? I get the 1 millivolt over 1 meg, which is 10 to the minus 3 over 10 to the minus 6, which is 10 to the minus 9, which is 1 nanoamp. So when I do AC analysis, and this is, if hopefully it's not confusing if you took 320 from me, we will get rid of the DC sources, and we will only look at the resistors or the AC components to calculate what the AC signal is. Does everybody follow that? Here's why. If I have a DC source, a DC current, I don't get any AC current in that, so why should I put it in my AC analysis? Just to make it more complicated and make me work harder? I don't want to do that. If I have a DC voltage source, why would I put it in my AC analysis? It doesn't change the voltage. I can't change the voltage across the DC source, so why would I put it in my AC analysis? Now when I go calculate the overall response, it'll be the AC plus the DC, but just to calculate the AC, I don't need that DC stuff. Okay, so let's go prove this. Okay, so let's go, and remember what I want to prove is with no voltage across it, I'm not going to add that 1 volt DC, I get 10 microamps, and with the voltage across it, I get, with 1 volt across it, I get 1 meg. So now, one of the issues and what I'm going to do here is I want you all to be very proficient with LT Spice. So if you took 621, 421 from me last semester, you might not even remember how to use LT Spice because all we did was cadence stuff, okay? So make sure that the goal here is not just to give examples, but also to ensure that what you have are references that you can pull up and use in the future when you're doing your homework or whatever. So I'm going to show you different analysis. I'm going to give you different ways of doing things, all that stuff. All right, so first off, before I even do that, how do I find where LT Spice is? I go to CMOS EDU, I click on LT Spice, and then I notice, hey, if I have problems in the book, all of those simulations in the book are already found right here. I don't have to redraft everything from scratch. Is everybody clear on that? Okay, so there's work problems from the book, there's examples from the book, there's past lectures and past quiz stuff. So, and then I can go install LT Spice right here. There's a Mac version and a PC version. Okay, so I've already done that, and yesterday I made sure it was up to date. So I'm going to open this from scratch. Now I'm going to do this from scratch, but most of the time we won't do that. We're going to just take something that already exists and copy. Okay? So I'm going to do File, New Schematic, because I tend to be forgetful. I'm going to do right at the beginning, Save As, and then I'm going to go over to the desktop, and I'm going to go into our examples, and I'm going to call this LEC1 _ example 1. And I'm going to go do a Control G to show the grid, and then I'm going to go grab a current source. So this little AND gate gives me component. So I'll go to current, Boom, plop that down, right click on it and give it a value of 10U. Then I'm going to go grab a resistor here and right click on it and give it a value of 1 MEG, not 1 M, because 1 M is what? Milli. And we don't want to give it 1 milliohm because then we'll go crazy trying to figure out why things don't work. Okay, and then I'm going to wire things up. So I'll get my little wire tool here. Now, how do I do a IV plot? What do I need to add at this point? Okay, this is the circuit, but I can't do the plot with what I have here because I'm not able to change the voltage. So what do? I want to add a voltage source. Okay, that voltage source isn't part of the circuit, but that's how I change the voltage across this circuit so that I can plot the current that flows. Okay, so I'm going to do that. I'm going to go add a voltage source. Boom, I'm going to call this VN just to... Okay. Now, there's a couple problems here. Let's give it a value of 0. We're going to change that in a moment, just so it has a value. There's a couple problems here. One, I want to sweep this voltage. I drew it on the right, now we're drawing it on the left. It's the same. I want to sweep this voltage from 0 to 1, because I'm not going to add the offset here. I just want to see it go from 10 microamps to 1 microamp. So I can add the sweep. But if I look at my schematic here, and I want to plot the current that flows, let me just show you the problem. So I'm going to go to it, poke the run. Let's save first. I'm going to poke the running man. And I'm going to go to DC sweep, and I'm going to sweep VN from 0 to 1. Oh, you know what else I didn't cover? What? Oh, thank you. A thought just popped into my head. I didn't cover the homework guidelines. Okay, so does anybody not follow that? I'm going to sweep VN from 0 volt to 1 volt. Now that's not part of my circuit, but I'm putting that into control. Now, here's the issue. There's two issues, like I said. The first one is there's no ground. So I got to put a ground in. Does it matter where I put the ground? Well, if I put the ground up, there's only two nodes, this node and this node. If I put the ground up here and I plot the node voltage here, what's that voltage? 0. So since I'm saying the voltage applied between here and here, I want to plot this voltage. So I'm going to go ahead and put the ground over here. Why isn't the ground important here? Why? Can anybody tell me, how does it influence the circuit? Let me ask a simpler question. How much current flows down here? Nothing. It's just a reference, right? But you got to have ground in your circuit. In fact, in most circuits, if you have current flowing on your ground, that's bad. And what's the common thing you all have in your house? It checks to see if current's flowing on a ground. Yeah, ground fault interrupter, you know, little thing in your bathroom, the set, reset. That thing's purpose in life is to say, hey, is there any current flowing in ground? Okay. So, I'm going to hit run now. And I'm going to look at the voltage here. And if I plot the voltage here, what do you think I'm going to see? Yeah, I'm plotting. This is my controlling voltage, 0 to 1. That's what I'm sweeping here. If I plot this voltage, oops. If I plot this voltage, then I'm going to just see a line with a slope of 1. But I want to plot the current that flows into the circuit. But how does SPICE define positive current flow? Through a voltage source. Positive to negative is positive current flow. So when I plot this, I'm going to see negative current. I'm saying it going minus. Does that mean I did anything wrong? No. Just means I'm not plotting it correctly. So I could come up here, right click and say minus. I could come in here, let's do it this way. Let's get the little hand and stretch thing. So get this and then stretch this. And then I'm going to get the little clipboard here and copy. And then I want positive current flow to be from plus to minus. So I'm going to do a Control R. Look down here, Control R. Until it goes from plus to minus. I'm going to call this V measure. And let me ask this, what is equivalent circuit for a 0-volt voltage source? It's a short, yeah, it's a wire. Okay, so does it influence the circuit? Nope. So I hit save, I hit run, and then I go plot the current through here. Notice the arrow's in the right direction now. Boom, full credit. Now, I'm going to pause for a moment, just because I'm assuming you've forgotten how to use this, and just make sure everybody's on board. If you look at what's in this folder, which I will post to the course webpage, you'll see there's these raw files and all that. I think I have this set up so that it automatically deletes the raw files. Okay, so in the end of the semester when you're doing your project, don't send me a 25 meg raw file, delete it before you go in, all right? But what's that? Oh, it did? Okay. So let's go put it, since I don't think we have any ones that are going to take long to simulate here. Let's go back to, yes, hit OK. Now notice when let's do it, let's quit. So let's save this and then go. And then now I rerun the sim. I go home tonight and go, I didn't understand a damn thing he did today in class. And you pull this up and you hit run, and it's not plotting, right? You want it to plot automatically, so I will try to remember to select this window and then hit save. And then when I'm done, there's this little plot file here that'll automatically plot things so that when I rerun the sim, there it is. Does everybody see how it goes from 0 to 11 just like I said? Any questions? All right, so I want to now do examples for the rest of the lecture on homework problems. And to start out, I want to work some of the homework problems so that you're all set up and that you do well on your first homework assignment due on Monday. Question? Before I do that, let me just cover... Uh-oh, that scares me. Okay. Did everybody see what happened there? When I hit the icon, it said 7 seconds. Okay. So let's go do the old homework thing. Where was our course web page? Right here. Homework. Guidelines. So again, everybody knows that the homework I assign that has an A in front of it's not from the end of the book. It's from the course book web page. That guy's demanding, man. All right. So homework's due at the beginning of the lecture. One of the funny things I pay attention to everybody in here that I can see. This classroom's a little bit hard for me to see everybody. But if you're working on your homework, I can see it. Come on. All right? So don't do that. It's due at the beginning. Don't tell me, well, I'm trying to make it pretty to follow your guidelines. Hint, I don't care. It's due at the beginning. Use only one side of the sheet of paper. Turn the homework in folded lengthwise. You will see that the reason that I do that is then when we write the grades, they're in the inside. When I hand back the homework, which I'll do at the beginning of every lecture, and your quizzes, turn in the quizzes the same way. Your grades on the inside. That way you know you're identified by your grades on the grade sheet, because I don't put any other IDs there. But if you show everybody, hey, I got a quiz, I got a 7 on quiz 4, and you were the only one in the class that got a 7, then everybody in the class that knows that can go look, oh, let's see how you're doing. Oh, you're not doing too well. What's wrong? All right. So you have to turn the homework in. Put your, some of these, I mean, look at the homework solutions, for example, on how to do the homework. When you do the homework, you have to put the problem number statement there. You know, if you don't like writing it out, just print it out and then paste it and put tape on it and put it on there. Your simulation should follow and be integrated with the problem solution. You can see I have all these different things. I like it when you write on the homework and say, here, this matches, this works. I like using a pencil and writing. I don't like you wasting time with computer animated drawings and stuff. It's really easy to print it out and just draw on it. I like handwriting. I'm not a fan of, as you can tell, PowerPoint. I like to write it out myself. Yeah, just go through these on your own. Don't give me grief, and I'm better than everybody else. I don't need to follow these guidelines. You'll see that the grader works really hard in the class, and so if everybody's throwing things all over and the grading isn't consistent, then it makes it an unreasonable amount of work. And then also when you have problems and you come in for help, if the homework problem's right there and I can read it before I answer your question and follow what you're doing, it makes it easier. All right, I know I didn't go over that very thoroughly, but I don't want to spend the time. All right, so we'll see how much fun we have on the first homework assignment. Talk to people that have taken me before if you need an example, I guess. What's that? Or drop the class. Yeah, that's another one. I'm going to drop your class, I know, and okay, great. That's less work for me. Less to grade and less questions. And I know I shouldn't say that, should I? That's not nice. All right, so let's go look and do a couple of the homework problems. Okay, so let's extract here. When you look at the homework, this is another one I get every semester. There's 2 chapter 9s. There's chapter 9 from my mixed signal book. And there's chapter 9 from this class. Don't go to the chapter 9 of the mixed signal and then send an email, hey, I can't find the homework. It's not there. Go to the other file. It's in this one, all right? So let's go and let's work. Let's do a few of these first problems. You'll see the ones that are due are these 2 right here. They're not meant to be super challenging. They're meant for you to learn how to follow the homework guidelines and use SPICE and have you a nice gentle acceleration. What's that? What's a triangle? Oh, God. Don't joke with me about that, man. You'll give me nightmares. All right, so I'm going to do these first few problems. And let's see. So estimate the AC current flowing in the following circuit. Okay, so let's go through this step by step. How much AC current flows in here? 0. How much AC current flows in here? 1 millivolt divided by 5 meg. So what is that? Isn't it 200 nanoamps? Let's write it out, and then let's get the old calculator out here. 0.2 nano? All right. So let's see, we had 1 millivolt, 5 micro, 5 meg. 1 millivolt, 5 micro, and I'm not going to be lazy. I'll draw it all connected together. And then 5 meg. AC current lowercase is what? Yeah, 0. The current that flows through here. Which is, yep, 0.2 nano. 200 picoamps. Questions? All right, that was A. Does the 5 microamp current source affect the amount of AC current flowing in the circuit? No. What is the DC voltage across the 5 meg resistor? What is the DC voltage across the 5 meg resistor? And why? It's 0. What's the AC voltage right here? 1 millivolt. Okay, wait a sec. When I look at the circuit, I ask myself, I don't go, oh, there's this, I think, is there any constant push into this resistor from anything in here? Oh, wait, I said it wrong. Is the DC voltage 0? It's 20, well, wait, is it 25? Okay, so let me look at this again. I'm looking at what's the push into the 5 meg. If I have this DC current, does it flow in the 5 meg only? Where it goes and flows over here, right? Because it's shorted out. If I remove this, then that current flows over here, right? And then what's the voltage here? Okay, so here's how I think. This is my straw. I'm going to take a drink out of this. If I take a drink out of this 5 meg, my drink is going like this. To get the drink of soda out of the straw, do I need a positive suction or a negative suction? Do I blow into the soda or do I suck the soda out? It's out, right? So is this going to be a positive potential here or negative potential? Negative. Minus 5 microamps times 5 meg. Wait a sec. I know the voltage, if the current's flowing like this and it's I, is 5 meg times I. But wait a sec. This current is being pulled in this direction, so it's minus 5 microamps. It's going in the opposite direction of that 5 meg. So it gives me minus 25 volts. Does anybody not follow that? I don't want you, this class, to see this. If you see a resistor, and it's R, and you have a current that flows back like this, well, the only thing I know is Ohm's law, which is V, R, I in this direction, which is R times I. Well, if I flip the current around, well, now this becomes V equals R times minus I. So I get a negative potential. Okay, so with this circuit, what's the voltage here? DC voltage. 0. Does anybody not see that this source, okay, let me give you a simpler way of looking at it because I'm seeing people feel pain. Okay, that's an AC source, right? The voltage across this from here to here is always 1 millivolt AC. I can't change that. Can I put 5 volts or any DC voltage across there? No, it's fixed. That source is 1 millivolt. Anybody not follow that? So if I ask what's the DC component there, the answer is 0. And in fact, if I was going to do a DC analysis, I would short out the AC source. And hey, wait, that's what I did when I learned Circuits 1 and I did Thevenin. So I looked at one voltage source at a time and I shorted out the others. Or for currents, I open them up. We're going to sim this, so we'll make sure it's correct. Anybody not follow that that's DC, because all of this current, which would probably be the next part, the DC current that flows through there is 5 microamps DC. What's the DC current flowing through here? 0. Clear as mud? Alright, so let's see what we have next. We'll see on the quiz on Monday. If you're getting it, it'll be like, this didn't challenge me. If you're not getting it, I put this on there, I'm like, I don't know what to say. Alright, so let's see. What's the AC voltage across the 5 meg? 0, because this is an DC short. So I replace that with the DC short. What are the DC voltages on each side of this resistor? 0, 0. Where does the DC current flow in the circuit? Through the 1 millivolt. Use a transient spice simulation to verify your answer. What happens in the circuit to the voltage across the resistor if you remove the AC source? Verify again with spice. So if I remove this source, how much current flows in the resistor? 5 microamps. What does this voltage become? Because I'm taking a drink of my soda. I'm going like this and pull minus 25. So let's go do the sim now and verify. Any questions? Okay, so let's go back, and because I'm incredibly lazy, I will go and open up this, and I will do File, Save As, and make this example 2, and then change this to 5 microamps, and change this to 5 mega ohms. And I'm going to get rid of this because it confuses me. And then I'm going to change this, and I'm going to go to Advanced and set the AC amplitude to what? Okay, 1 millivolt, but it said use a transient. So this is where it gets confusing. For transient, AC, this part, doesn't mean anything. So I'm not going to put anything there. What I'm going to do instead is I'm going to go to Sine, and I'm going to put DC offset 0, amplitude 1 millivolt, and then I'm just going to pick, and this is where you run in, the students doing the homework, oh, it's easy, and then you realize, I don't know what frequency to use. It doesn't really matter. There's nothing in there that's going to cause you grief, so I'll just pick 1 kilohertz. Okay? You don't like that? Let's pick 1 hertz. 1 hertz. Okay, and I'll connect the wire up here. Then I'll get the big hand, and I'm going to move this out of the way. Let's move this one over so it looks, it's the same circuit, it's just, I want it to look just like it did before. And then, you know what, before I even do this sim, I'm going to hit save, and then I'm going to actually change this. Or actually, let's not, let's just run it. We'll cover operating point later. Okay, do I have a analysis in the sim? Well, before I even do that, does anybody have any questions on drafting the schematic? What if you need extra help with LT Spice? There's tutorials on the website. Just watch the videos or go through the tutorials. All right, so let's hit run. What's that? Oh, yeah, I don't want to do that. Let's get the scissors out and hit save, and then hit run. And then I want to do a transient. And what do I put here for my stop time and why? Okay, what's the period of my sine wave? 1 second. So how many periods do I need for good homework score? Let's say 5. Yeah, let's go 4. Okay, 4 periods of the sine wave. So I hit OK for 4 seconds. Hit OK. Oh, let's make sure I get a nice little sine wave there. And I do. And I ask you, what's the DC value there? 0. Okay, we're going to change that in a moment. Let's hit save. What's the current that flows in the, so let's back up. How much AC current do I get flowing through here? So let's show that. Let's go to Add Plot Plane and click on this. And I see, well, it would be nice if I see it. Let's make sure top is, say, 10 micro. Tick is 2 micro. I want to get good grades on my homework. So 0. You just want to pass? I didn't hear that. All right, so what's the AC current flowing through there? 0. Okay, and now if I ask, what's the AC current flowing through here? Add plot plane. And was it I calculated? 200 pico, 0.2 nano. Woo, yay. So I hit save. And I've done it the way the problem writes, but I want to make sure that I'm correct. So here's what I'm going to do. Before I move on, are there any questions? Yep. Yeah, so if you want to change the colors, go over here to color preferences, and then you can change. So I changed it to have a white background, and you want to do that too, so when you print your homework out, you're not printing out big blobs of ink. Okay? Any other questions or comments? Okay, so I want to just show that I know what I'm doing in this problem a little bit more. So I want to do what is the currents that flow for DC operating conditions by doing a dot operating point analysis. So I'll go over here. I'm going to do a file, save as, and then, hey man, I'm not that boring, right? All right. You are, I am. All right, so I get the scissors out, go over here, and then I'm going to hit, actually I'm going to do it this way. I'm going to press this, and I'm going to type it out manually, which is the way I like to do it rather than, and this is just dot operating point. Now I'm going to hit save, and then run. And it tells me what the node voltages are, but if I go over here, what's the DC voltage right there? Where do I see that? Boom. Okay. What's the DC current flowing through here? There it is. No, just like I said. What's the DC current flowing through here? 5, just like it shows. Why is it minus? Because SPICE defines positive current flows from plus to minus. That doesn't confuse me. I know what I'm doing. Okay? Any questions? What was the last part of the homework problem? Remove the source. So let's go ahead and hit save, close. How am I going to show that? I could do a dot operating point, remove the source. I'm not going to do that. What I'm going to do instead, so I'm going to get this, I almost made a mistake there. Save as, example 4. And then I'm going to get the scissors out. And then I'm going to cut that out. Move this guy over. And then what do I expect to see here? Okay, so this is important. When you're doing in a digital lab and you're working in your microcontrollers or you're doing your senior design project or whatever, and you have some input, and the input may need to have a fixed number of zeros and ones. Does everybody follow that? You can't just leave the input floating. Okay, if you leave it floating, it might go to an intermediate value where it's not a good logic 0 or 1. You have to physically, if you say it's a 0, you have to physically ground that input to put in a 0. If you don't do that, you will be chasing your tail. This is the exact same thing. If I don't have my input here to pull this down to ground, to pull that 5 microamps, and I go now plot this node, I get minus 25 volts because I have no input. It's not, oh wait, if I put a short or a voltage source to ground is not the same as putting nothing there. That's the key point I'm trying to make. Does everybody follow that? You got to put, even though it says no input, you got to connect it somewhere. Okay? All right, so there it is, minus 25. Let's save that. Okay, any questions? I want to do one last example before I quit. It's all making sense. The pain is low. Okay. Till you do the homework assignment? Come on. On Sunday night, all right. And you all are going to watch the lecture on Friday, right? Because we will have a quiz on Monday. What's that? Same time as this. Yeah, so if you look, it'll always be the same. It'll be the same. If you click here, I'm very big on communicating. January 23rd, same room, same time, no homework. Attend if you can. If not, watch over the weekend. And I'll probably do this 2 or 3 more times this semester because I don't believe in cheating you out of lectures. So it'll be the same deal. All right, real quick, and we'll see how fast I can do this. Let's just do this. I want you to plot the IV curves for this circuit. This is likely be pretty close to what the quiz is. Tell me how to begin. Yeah, plot the IV curves. Tell me what to do first. All right, now what? What's the easiest? Okay, this is where you're trying to determine what's going on here, so you're going to apply an input voltage. What's the simplest input voltage you can apply? 0. There's 0. Does everybody agree with that? So that's at this point right here, so V is 0. So I need to calculate how much current that flows there. Okay, so let me ask this. Since we're running out of time, I'm going to do this fast. How much current flows here? How much current flows here? 1 micro. What's this voltage? Okay, it's the exact same thing, and I'll do this throughout the semester. When I put a voltage source there and I ask, what's the voltage across the voltage source, your brain shut off, and it's always the same thing, whatever the value of the voltage source is. It's 2 volts. Okay, what's the voltage here? Let's put our reference here. 0. So what's this voltage? When you say the voltage is at this node is 2, it means that node to ground is 2 volts. So it's 2 volts. So how much current flows here? Let me see. Let me redraw it. 1 meg, 2 volts. So that is 2 over 1 meg, 2 microamps. So the current that flows here is 2 microamps. So I got 2 going in and 1 coming out. So what is this current equal to? Minus 1 microamp. So my first point is right here, minus 1 microamp. Okay, real quick, I'll do one more point and then you'll have to sim it on your own. What's another value that I could do? Okay, wait, is this a linear or nonlinear circuit? Linear. So once I get 2 points, what can I do? Draw the line. Okay? So let's put 2 volts. Good answer. Why would I want to put 2 volts? Yeah, that's 2 volts. What's the voltage here then? Okay, what's the voltage across the resistor? 0. This side's at 2. It's always independent of what I put here at 2 volts. This side's at 2. 2 minus 2 is 0. I get 0 current through the resistor. So what is I equal to? 1 microamp. And so I got this. And I'm guessing that at 1 volt, I get 0. And yep, that's what I get. Any questions on that? So when we have our little quiz here on Monday, you're not going to be challenged to work one of those problems. When we come back on Friday, we're going to talk about the square law equations. Have a good day. See you on Friday.